Hello and welcome to part 5 of Dev Maths and Stats Refresher Course, Lecture 5, when we're going to move on to optimization now without constraints. So this probably is the most common use of differentiation, finding maximum and minimum points. And that's because of this central idea that I've mentioned before, which is at a maximum or minimum point of a function, the gradient of the tangent, which could be the tangent line or tangent plane, is 0 in all directions. And it's the all directions which is the problem, because as you add variables there are many more directions you can go in. We need to just look back at the examples above. If you look back at the function f above, clearly there is a maximum at 4. Let's just check that graph again. See. So if you just said, here's your resource you're allocating, find the maximum output 4, maximum utility, whatever, 4. But let's say that in the more realistic world where you're running a project, you can't just pile in unlimited resources. If your resources were limited to 3, you only have 3 available, and you have the same utility function, then the optimization problem there would be, okay, the answer is go for 3. That's the maximum we have available. At this point, the gradient isn't 0. Whereas at this unconstrained optimum point here, the gradient is 0. So it's in the unconstrained case where we can look for gradients being 0 as the clue. Let's find where we were. So here, if we set ourselves a limit, a constraint, the slope may well not be 0. So that second case, when there's a limit on some variables, it's called constrained optimization. It's more generally useful and more realistic. But first of all, we have to look at unconstrained optimization. So in this case, the variables can take any values. And in this case, the gradient of the function is always 0, whether there's a maximum or minimum point. Now this gives us what is often referred to as first order conditions for an optimum. Okay. So the derivatives of the function with respect to every variable must be equal to 0. So if we look back at the two functions we had above, there's function f and we differentiate that. That's the derivative, and this must be equal to 0. If you solve that, you find that x is equal to 4, so just rearrange this and solve it. X is 4, so that confirms the visual impression that the optimum point is at 4. For the other function, the one with 2 variables, you have 2 partial derivatives which must both be 0. So here you're getting to this must be 0 and this must be 0. So here you're going to have to use simultaneous equations. So you can have elimination, substitution, or now you'd really love to use matrix inverse or Cramer's method, which could solve these. However you do it, you can find that x is 16 and y is 30. And if you have a quick look back at that graph, y is 30 and x is 16 is indeed where this comes to the minimum point. It's not easy to see, it's about here. That's where it reaches the minimum. Okay, so it does work. We can now hide this section. If you're okay with all of that, you can leap onto the next video now. We're going to look at the idea of second order conditions, how you tell whether you've got a maximum or a minimum or something else. But I'm going to spend some time in this video working through some problems by hand, well, by hand and calculator, just for people that are interested in that. So if it's very easy, please just don't feel you have to watch this, just whiz forward. So I'm now just going to copy these and paste them into the whiteboard and go through these one by one, just so you see the steps if you want to. Otherwise, go forward, because it could be boring if you don't want to follow all the steps. So here's the first one. Just see if I can blow it up a bit because it's a bit small. Okay, so there's our function. So we're just going to take this and differentiate it. So the first order condition, right, shorthand is that this must be equal to 0. So I'll differentiate this. We might have 9x squared minus 8x minus 5. It's got to be equal to 0. 9 squared minus 8x minus 5 equals 0. Okay, looking at that. 64. So it's not going to factorize, so we're going to use the solution for quadratic equation. So we find that x is going to have to be equal to, I really will give you the full details. What I'm using here is this equation that we're looking for, minus b plus or minus square root of b squared minus 4ac. And that's going to all be divided by 2a. So that is, I'm going to put into here, minus b, so that's, we've got 8 plus or minus square root of 64 minus 4 times a times c divided by 2 times a, which is 2 times 9. So it's 8 plus or minus, this is the 2018-244. Squaring that, so that's what I was looking at before, so that means there's no neat solution, so you can't factorize it. 18. So here I'm going to zip off to a calculator and come back with the answer in a moment. So here's what I get for the two values of x. So it could be negative 0.42 something or positive 1.31. Now we're interested in the maximum and minimum values of this function u. So we need then to substitute this back into u to see what are the two values for maximums and minimums. So again, I'll want to type that into a calculator because I can't do that in my head very easily. So I find that u is equal to, and these are the two optimum points, or I think are the optimum points. Okay, so you can see these are the two points here. So the points at this, when x is this negative number, that's the value of the function u. When x is this, that's the value of the function u. Problem is, have I found really maximums or minimums? I don't know. So if you go forward to the second order conditions, you see how you find out this, but it's quite useful to know how you would check it by hand, just to get a concept of what the second order conditions are doing. So one way of doing this is to look at, see this value here of x, that's a candidate. So if I look at a value just below this, so if I look at, well, actually, okay, I'll stay in the same order. So just above and just below this. Okay, so 1.3 would be, well, let's go 1.2, so there's enough leeway. So let's look at other values of u. If u is equal to this, or just above that would be 1.4. This one just below this, let's go for negative 0.43, and above it negative 0.41. So that's just either side of this and either side of this, and then I'm something wrong. This is going to be x. These are some values of x, and then here are the values of u that go with that. So again, nip off the calculator and see what we get for these values. So here I've calculated some values and pasted them back in. So they link up like this, hopefully. Those. And then these, remember, link up like these. These are the ones we think are the maximums or minimums. So if we look around this one, just below and just above this one, so that's these two values here, either side of this, compared to this one here, they're both slightly higher. Yeah. They're both slightly higher than this one. So that suggests that this is a minimum point. Yeah. because if you move slightly to either side, then the function increases. So this must be a minimum point. But this one here, if I move slightly to either side of this one, just below or just above, I find the value of the function is 7.2. Oh, it's just slightly decreasing. So in both directions, below and above, it's slightly decreasing. So here, in this situation, I'm decreasing each other. So this one must be a maximum here, and this is a minimum. So this is a max, a local maximum, and a local minimum. Because anything I change here increases the function slightly. Anything I change here decreases the function slightly. Okay. So you can get an idea of whether it's a minimum or maximum just by looking at nearby points. Okay, let's go on to the next part of this. Don't forget this, if you're finding this is all very, very slow, okay, so we're going to go on to this one. So I'll just paste this back over to this one. I need to clear this. Clear it. Okay, let's paste this at the top. Okay, so start as before with the first order conditions. So differentiating first with respect to x, we're going to have to set this equal to 0. So here we've got 2xy. That's right, yes, so I was just checking I've got the right one. So differentiate this, we have just 2y from this part. From here we have minus 4x from this part. This is just 0. This is just plus 58. Should be equal to 0. Okay. That's the first one. And the second one, derivative with respect to y. Similar thing is that we have 2 hex. This is 0. This one just gives you minus 2y. And this is 0, and this gives you minus 22. It's got to be equal to 0. So we have a pair of simultaneous equations to solve to satisfy the first order conditions. You could use elimination method, substitution method, but I think if you're watching this, I'm sure that's for one reason only, which is that you're desperate to do the matrix-related methods. So if I transform this into a matrix form, you'd have to first of all arrange it neatly. So you have, let's make some room by putting it up here, minus 4x plus 2y is equal to negative 58. And then here you have 2x, that's already in the right order. 2x minus 2y is equal to plus 22. So now you have it. This is just to get it into the correct order. Now when you have it, it's very tempting just to add these together and solve by substitution, but let me show you the matrix method just for revision of that. This means that the matrix form for this is negative 4, 2, 2, negative 2. So times xy is equal to 58, 22. oops, in fact that should be negative 58 there. So now we're going to solve this by finding the inverse of this matrix here. So answer for x, y will be equal to inverse of this. So that's negative 4, 8. So the determinant is 4. So 8 minus 4 is 4. And then multiply that by the rearranged cofactors. So minus 2, minus 4 here. And these change to negative. So switch these, changed from positive to negative. Multiply by the negative 58. And the 22, and you should find something that looks convincing, hopefully. So I'm going to have positive 116, yeah, positive 116, and then subtract 44. $74, 22, okay. And then you want again 116, and this time subtract 88. 28. So this is going to give you 618. So it looks like x is equal to 18 and y is equal to 7. Okay, now just nip off to calculator and grab a value for the function h. So h at 18, 7 is equal to, okay, we get exactly 160. So by looking at the form of the equation, probably we can tell that it's more likely to be a maximum, but if you can't tell that, or if you can't use the second order conditions, we can check as we did in the previous one. And I think to save writing out all the options here, what I point out is that the difficulty of doing this is that, okay, we can just look either side of this x. It's like we could go to that 18.1 or 17.9, and we could look at 6.9 or 7.1 nearby here, but we also have to go in all the other directions as well. So if you've got the point, if this is the point 18.7, as well as looking at the point here, which should be 18.17, and this point here, which should be 7.1, those coordinates. We also want to look here, which should be 18.1, 7.1. We also want to look here and here and here. We want to look at a number of points around this point to see, is the function increasing or decreasing in all these directions. So what I've done is I just go to the calculator and cheat and get some quick answers so we can have a look at those values. Okay, and as you can see what I've really done is just define the function in Maple and then put these numbers in. So I've looked at 18.17, 18.17.1. So I've gone effectively to all the points around near this point, 18.7, and put it back into the original function. And I found in every single case, the value of the function has gone down slightly. So wherever I move, the value of the function is going down. So that means that this is a maximum. Doesn't completely prove it, because it could be, if the function was a very strange shape, that it goes down here, and up in this direction. But that would be unlikely, but it's a possibility for some complex functions that it could be going down in these directions and up in this direction. But having checked those 9 points, I'm fairly happy it's going to be a maximum. And in the second order conditions part of the video, you'll see how you can show that more rigorously. Okay, now I'm going to just make some more space on the whiteboard and then do the last one. Again, if you're getting bored, just zip forward to the next section. This is just for people that like to see every step. So Here's the next one, function k. So I've copied that and pasted it in. If I can find the whiteboard. Okay, here we are. I'm going to find the first order conditions, which are that both the partial derivatives have to be 0 as before. So differentiate with respect to x, we're going to have a 2x here. We have a plus y, nothing from here, minus 55 here. It's got to be equal to 0. Let's just check that again. I find it hard to read this Excel format sometimes, so yeah, indeed, I thought something would go wrong. So you have 4x there. 4x, just an x there, nothing, 50, minus 55 there, and nothing. And then for y we have nothing here, plus x there, x there, and 2y there, or minus 2y, sorry. And any numbers? Yes, 20 there. So these are the two first order conditions. So I think we'll put these straight into matrix form this time, cut a few corners. Hopefully you can see that we're going to have a 4 and a 1 and a 1 and a minus 2 for the coefficients of x and y. And so we're going to have 55 and negative 20. So I enjoyed doing this in a live class because the live class will tell me all the errors I'm making, and I won't go on making the 4, 1, 1, minus 2. Okay, it seems pretty good. So the previous one we solved with inverse matrix, so this one let us solve with Cramer's rule, which tells us that the value of x, and the nice thing about this is it's totally automatic. You're just going to write down the answers based on the determinant. So first you make this matrix, so you take 55, minus 20, 1, minus 2. So that's the first alternative matrix with the first column replaced by this. That'll help you find x. And you have to divide that by the determinant of the whole matrix, the original one, 4, 1, 1, minus 2. Remember, this means determinant of, and then y is going to be y is going to be with the proper equal sign the other alternate matrix, which is 155 minus 20 divided by the same original. X is going to be equal to, we need the determinants of all these matrices. So the easy one is minus 8 minus another 1 is minus 9. So they're both divided by 9. Now y is equal to something divided by minus 9 effects. So we've got minus 110 plus 20, which is 90, minus 90, sorry. And here we got minus 160, gosh, that sounds a bit excessive. Is it 20? Yeah, minus 80. Minus 80, subtract another 55 is minus 135 is minus 135. Okay. Okay. We simplify that. We're going to have x is 10 and y is 15. Okay. Now, similar to the above, we now need to substitute this back into the function to find what the value is of the function. So here we've got function k. So the value of function k, that's 10, 15, is going to be equal to calculator reckons minus 65. And then to tell whether this is maximum or minimum, I'm going to take again the point 10, 15. So that's the point 10, 15 here. I'm going to look at some points all around. Slightly higher, lower in the x direction, y direction, diagonally like this, to see what happens to this if I go in different directions. So that's this is my points 10, 15 here. So I'm going to see what happens if I go in different directions from there to see whether this is a maximum or a minimum. So I'll just go and get some calculations in Maker of those local points and then paste them in. Now, this is getting more interesting because we can see that compared to this value of 65, if I move in some directions, it goes up above 65 slightly, 65.01 here. If I go in other directions, it's just pretty flat, nothing happens. If I go in other directions, it goes down. So this is a bit odd. Going in the x direction, it's so if I put some reds for when it's going down, if this is x direction, it goes down in this direction, and it goes down in this direction, and then it goes, and greens are up in this direction, up in this direction, and up in this direction, and down in these directions. I think, yeah, so this 1, 2, 3, 4, 5, 6, 7, 8. Oh, I'm not counting it properly, but in this one, the final one is no change. So it's going up, sorry, down, down, up. On this one here, it was going no change. Down and up, and then no change. So it's going down in these directions and up in other directions. Some directions no change. So it's confusing to see what's happening. So this is one of these points that, like we had in the very first lecture, and we can see another example of it back on this diagram here, where we're in a situation like this, where if I just look at the original point, we're here. So we found a point which is flat. So if you look at the f tangent, it's flat. If we look at the x tangent is flat. In the y direction, it's flat. Oops. Yeah. So we found somewhere that's flat. Even the tangent plane at this point is flat. But unfortunately, as we move away from it, in some directions we're going up or down. Sorry, in some directions we're going up. In some directions, you can stay on a contour and it won't change. So we found a point of inflection, like a saddle point. So even though the first order conditions are satisfied, so this is satisfied, we've found a value, but it's not a maximum or a minimum. And at the moment, you can only test by looking at different points near it. So we need a better way of doing that, which is why in the next section we go on to look at maximum or minimum second order conditions. Okay, sorry that was a bit long. I hope that you only watched it if you wanted to watch it and you didn't feel you had to sit through that. But I hope if you did sit through it, and then you found something useful there. So thanks for watching, and I'll see you in the next video.